Hey everybody, welcome back to Mr. A's Geometry course. Today we're going to be going over sections 3.3 and 3.4 of geometry, which is going to have to do with proofs for parallel and perpendicular lines. Now previously we've gone over some new properties that are involved in proofs, things like the substitution property and the transitive property and so on. We're still going to be using that kind of reasoning, that kind of logic in our proofs, but we're going to be adding these new things we've been learning in Unit 3, like our angle pair theorems, like corresponding angles being congruent. All right, so again, we're learning all about proofs here with our parallel and perpendicular lines. Let's get into it. In our first example here, we're going to be proving an angle measurement. So we're given that some lines are parallel. We're given the measure of one angle being 100 degrees. We have to prove that a different angle is going to be 60 degrees. So in our figure here, we're talking about angles 1 and 6. Angle 1 is given to us as 100 degrees. There's a few different ways that we can take that information to then prove that 6 would be 80 degrees. Let's see the route that this proof takes, right? Let's remember that the first statement in any proof should be your given information. That's why this says in our statements 1 and 2, line M is parallel to line N, the measure of angle 1 is 100 degrees. Those are the things that were given to us at the start of this problem. So my first two reasons in this proof will just be given. These statements are true because they were given to us. Next, we have the statement that angle 1 is congruent to angle 8. So let's look at our figure, 1 and 8. We need to be able to recognize these angle pairs on our lines. 1 and 8 are exterior angles. They're outside lines M and N that are parallel in this figure. They're on opposite sides of the transversal. Remember, this is alternate interior angles. And we've learned in this unit that on parallel lines, alternate interior angles are congruent. So those angles would absolutely be congruent to each other. Angle 1 is congruent to angle 8. We would say because alternate interior angles are congruent to each other. Alternate interior angles are congruent. In statement 4 here, we have the measure of angle 8 being 100 degrees. This is actually true because of our transitive property. And we might get a little nitpicky here because that's a congruent sign and not an equal sign. But we do see that angle 1 is going to be equal in value to 100 and to 8. So because both of those things are equal in value to angle 1, they must be equal in value to each other. That is our transitive property. Transitive property says measure of angle 8 is equal to 100 degrees. Our next statement says angle 8 plus angle 6 equals 180 degrees. Remember, as we do these proofs, we're thinking like lawyers. We're thinking, why is this true? How do we prove that this is true? Well, if you look at 6 and 8 in our figure, this is another angle pair that we must be familiar with, all right? Where 6 and 8 are located here side by side on the straight line, that is a linear pair. Linear pairs are supplementary. They add up to 180 degrees. So yes, it's true that 6 plus 8 would have to equal 180 degrees. And I could say something like linear pairs are supplementary to each other. All right, linear pairs are supplementary. I'm going to abbreviate that for time's sake here. Our next statement says 100 degrees plus angle 6 equals 180. Well, notice that's almost the same exact equation. The only difference is there's a 100 instead of an angle 8. And we already established before that angle 8 equals 100 degrees. So we've just kind of substituted that angle 8 for the 100. And that's literally what we did. We used the substitution property of equality here. Substitution property. Not property of equality, I think is what it said there. Just substitution property. All right, and then we're told that angle 6 equals 80 degrees. Well, that can be found because this is a solvable equation, right? If I want to get angle 6 alone here, I can just move that 100 to the other side of the equal sign to get that angle 6 is 80 degrees. I would be subtracting both sides by 100. And that's probably where I misspoke there previously. I was thinking ahead. This is the subtraction property of equality. Subtraction property of equality. Again, we subtracted both sides of the equal sign by 100 here to get angle 6 equals 80 degrees. That's our first proof done for today. Our next example looks exactly the same. It's because it is. This is the same given information. we're being asked to prove the same thing, that the measure of angle 6 equals 80 degrees. We're just going to see that in the proof we're taking a different route to get to that conclusion. We're going to be using different angle pairs to prove this because there are a bunch of different angle relationships that exist here on these lines. But as always, our proof is starting the same way, that given information has to come first. We know that line M is parallel to line L because it's given information. We know the measure of angle 1 is 100 degrees because it is given information. And now our third statement is where we differ from this proof and the last one. This says angle 1 is congruent to angle 4. Let's look at our figure and see why that's true. Hopefully we can recall from unit 1 here. 1 and 4, those angles are across from each other at the intersections of lines. My screen is freaking out right now, sorry about that. They're across from each other at the intersections of lines here. Those are vertical angles, which are always congruent to each other. Whether on parallel lines or not, vertical angles are always congruent. So for our reason 3, the reason angle 1 is congruent to angle 4 is because vertical angles are congruent. Vertical angles are congruent. So then we're told that angle 4 equals 100 degrees. Again, this is going to be our transitive property. And for now, just ignore the fact that that's a congruent sign, not an equal sign. We still have 4 and 100 both being equal in value to angle 1. Therefore, they must be equal in value to each other. That is the transitive property at play. Transitive property proves that the measure of angle 4 is 100 degrees. Next we have angle 4 plus angle 6 equals 180 degrees. So again, we're going to look in here at our figure and determine why this statement is true. All right, so where 4 and 6 are located, where my green dots are right here, those are in between lines M and N. They're both on the right side of our transversal. These are called consecutive interior angles. We learned that earlier this unit. And on parallel lines, consecutive interior angles are supplementary to each other. It means they add up to 180 degrees, just like it says that they do here in step 5. So I can say consecutive interior angles are supplementary. Abbreviating for spatial reasons. All right, next our equation here in step 6 says angle 1 plus angle 6 equals 180 degrees. Again, pretty much the same thing as step 5, except instead of an angle 4 here, we have a 100 degrees. So that's just been substituted again, like our previous proof. That is the substitution property at work. Substitution property. And then just like before, angle 6 is solvable here. We can get that alone by subtracting 100 from both sides to get angle 6 equals 80 degrees. That is the subtraction property of equality. There's our second proof of the day done. So in our first two proofs, we were given that lines were parallel, and we used that information to find the measure of angles. What we're going to do now is the opposite of that. We're going to know some information about angles, and we're going to use that to prove that lines are parallel to each other. So it says angle 4 is congruent to angle 5. Let me show you where those are on our figure here. 4 and 5 are congruent to each other in our example. My screen's bugging a little bit. So sorry. So our first statement is always going to be our given information. And remember, our first reason will always be that it was given to us. Angle 4 is congruent to angle 5 because it was given to us. Our next statement says angle 1 is congruent to angle 4. Well, if we look in our figure, angle 1 is congruent to angle 4. We know that because they're vertical angles across from each other at the intersection of these lines. So we know vertical angles are always congruent to each other. That is the reason 1 is congruent to 4. Vertical angles are congruent. Next we have the statement that angle 1 is congruent to angle 5. And again, this is going to be the use of the transitive property because angle 4 is congruent to angle 5. Angle 4 is also congruent to angle 1. So since 1 and 5 both congruent to angle 4, 1 and 5 have to be congruent to each other. Because they equal the same value, they must be equal to each other. That is our transitive property again. Transitive property. And then here's something that's a little bit new. Now we're saying that line M is parallel to line N. Okay, and what we're doing from here is thinking about the angle pair that was described in our previous statement. And we didn't write anything about angle pairs here on step 3, but 1 and 5 are an angle pair up here. 1 and 5, we'll notice, are the angles that are in the top left of their intersections here. 1's in the top left, 5's in the top left. Remember, we call these corresponding angles. And we've learned here in Unit 3 that corresponding angles are only congruent to each other when they're on parallel lines. So because 1 and 5 are congruent and they're corresponding, the lines that they're on must be parallel to each other. And here's this introduction of the new theorem. So when we learned that corresponding angles were congruent, we called it the corresponding angles theorem. What we're doing now is the reverse of that. Because we know the angles are congruent, we know the lines must be parallel, so this is the corresponding angles converse theorem. I'm going to do CORR just to abbreviate, corresponding angles converse theorem. All right, so most important thing here in this proof is that our converse theorems are going to be the things that we use to prove that lines are parallel, and we'll always use that most recent angle pair to do this. Now, one of the things that can be a little confusing, maybe some people say is frustrating about proofs, is that we didn't really need to get to the corresponding angles here because the information that was given us at the start, angles 4 and 5, hopefully you notice here, are alternate interior angles. All right, and we learned that alternate interior angles are also only congruent on parallel lines. So from the start of this, we could have used the alternate interior angles converse theorem to say, well, if these are congruent, these lines have to be parallel because alternate interior angles are only congruent on parallel lines. However, proofs can take any numerous amounts of routes to prove information. It can be done in a short amount of statements. It can be done in a large amount of statements. That's why we have to take these proofs statement by statement to fill in our blanks from start to finish. In this case, we did have to add a few angle relationships to get there. For this proof, we're actually given degree measures for 2 angles, and we're going to be using those to prove that line M is parallel to line N. So we know that angle 7 is 63 degrees. Again, this is true because it was given to us. We know that angle 1 is 117 degrees. Again, it's true because it was given to us. You notice here that those are kind of combined in the same statement. Sometimes that happens, sometimes they split it into the first 2 statements. This time, it's only one of them here that's given to us. Next, we have the statement angle 1 plus angle 3 equals 180. Remember, all these proofs follow that same structure of we're writing statements that are true and then providing a reason, some evidence that proves that they are true. Angle 1 and angle 3, we can notice here are a linear pair. 1 and 3 are side by side there on line T, a linear pair, and all linear pairs are supplementary to each other. So that's why we can state that angle 1 plus angle 3 equals 180 degrees. We can say this is true because linear pairs are supplementary. Linear pairs are, abbreviate supplementary there, okay? Next, we have something that needs to be filled in here for a statement, and the only reason it's true is because of the use of the substitution property. So remember, the substitution property is when you take equal values and you swap them for each other, and then you give an equation. So we have an equation here, 1 plus 3 equals 180, and we actually know that angle 1 is 117 degrees, so I can just substitute that for angle 1 here in this equation. I can say that the 117 degrees from angle 1 plus, there should be an M there in front of angle 3, measure of angle 3 will equal 180 degrees. So again, it's the same equation, I've just substituted angle 1 for 117 degrees. Our next statement says that the measure of angle 3 is 63 degrees. Well, that can be found from this equation. I can get angle 3 by itself by moving the 117 to the other side of the equal sign. That would be using the subtraction property of equality. We would subtract both sides of the equal sign by 117 to solve for the measure of angle 3 at 63 degrees. Next, we have angle 7 equals angle 3. I should say the measure of angle 7 equals the measure of angle 3. And we're going to be looking at our previous statement and all the way back here to our first statement, right? We have the measure of angle 3 being 63 degrees. The measure of angle 7 is also 63 degrees. Therefore, the measure of angle 7 is equal to the measure of angle 3 because they're both 63 degrees. They're equal to each other. Remember, this is the transitive property. If I say one thing equals 63 and another thing equals 63, those things must be equal to each other. That is our transitive property. So that property shows up a lot in our geometry proofs. Okay, and we are being asked here to prove eventually that line M is parallel to line N. Remember, all of our theorems that involved our angle pairs on parallel lines all mention things being congruent or supplementary, not specifically that word equals, right? So we're just going to rewrite this, but with a congruent sign instead. We know congruent means equal in value. So if they're equal, we can also say they're congruent to each other. We would say angle 7 is congruent to angle 3. And that's true because of our definition of congruent angles. Congruent means equal in measure. And now we can say, okay, on parallel lines, we have these angle pairs that when they're congruent, or we have angle pairs that are congruent only on parallel lines. So let's look at angle 7 and angle 3 in our figure. Angle 7, we'll notice, is in the bottom left corner of its intersection. Angle 3, also the bottom left corner of its intersection. This is that matching position angle pair that we call corresponding angles. So because my corresponding angles are congruent, my lines must be parallel. Corresponding angles are only congruent on parallel lines. Again, this is where we're using that converse theorem here. So we would say corresponding angles converse theorem. Because these corresponding angles are congruent, the lines that they're on must be parallel to each other. 3.4 is just a continuation of proofs. We're just specifically going to be looking at perpendicular lines this time instead of parallel lines. So let's start off with a little review about perpendicular lines. These are lines that intersect and form right angles. Right? Remember that we see right angles mostly listed with boxes, or mostly marked with boxes. We don't typically see like a 90-degree written inside the interior of a right angle. We just see the box that's provided for us. So in our next example here where we have to solve for x, we just need to notice that there's a right angle here at the intersection of these lines that makes them perpendicular to each other. And if we have one right angle, then all 4 of the angles here at this intersection are going to have to be right angles, right? Because of things like linear pairs here, side by side have to add up to 180. So if this is 90, this is 90. And we can also use things like vertical angles, like these two across from each other must be congruent to each other. So to solve for x, we would just set 7x plus 6 equal to 90. So those lines are perpendicular. The angles formed at their intersection have to be right angles, 90 degrees. So to solve for x here, I'm going to subtract both sides by 6 to get 7x equals 84. Then I can divide both sides by 7 to get x equals 12. Hopefully that's a good refresher for you on how perpendicular lines work. In our first proof here on perpendicular lines, we're told that line OR is parallel to line KN. So here's line OR, here's line KN. We know they're parallel because they have a matching amount of arrows on them, in addition to it being told to us here that they're parallel to each other. We're told OR is perpendicular to QT, so here's OR, here's QT. And again, in the figure, there's proof that they're perpendicular. Remember, perpendicular lines will make right angles where they intersect, and we have one here in our figure. And what we have to prove is that KN is also perpendicular to QT. So KN is this line down here. Notice that the figure, there's no right angles at the intersections there. We have to prove that there are indeed right angles there, that these lines are perpendicular to each other. As always, the proof starts with given information. This is the same stuff that was provided to us here. The reason that it's true is because it was given to us. Next, we're told that this should say measure. The measure of angle QPO is 90 degrees, which yes, we see in our figure, but remember we know this is true because perpendicular lines intersect to form right angles. So that's a reason that we can put in here. You can also argue that we could write right angles are 90 degrees. Could be a reason that we put in here. I'm going to say perpendicular lines intersect at right angles. Right? Next, we're told that angle QPO is congruent to angle PSK. So let's find these on here. Angle QPO was our right angle. Sorry, my software is bugging a little bit. So angle QPO is that angle right there. The angle that we're told it's congruent to here in statement 3 is angle PSK, which is that angle right there. And this is an angle pair that we've learned about here in Unit 3. That's that matching position 1, because QPO is in the top left of its intersection, PSK is in the top left of its intersection. These are corresponding angles, and because our lines are parallel here, we had a theorem that we learned that corresponding angles are congruent to each other. So that's the reason these angles are congruent. We're going to say corresponding angles are congruent on parallel lines. All right, next it says the measure of angle QPO is equal to the measure of angle PSK. Right, this is just for equality, right? This is essentially the same statement. This says congruent, but we know congruent means equal in measure. So we can say these things are equal to each other. This is the definition of congruent angles. Definition of congruent angles. Statement 5 says the measure of angle PSK is 90 degrees. And this is going to be yet another use of our transitive property, because notice here that 90 is equal to the measure of QPO. Angle PSK is also equal to the measure of QPO. So PSK equals QPO, 90 equals QPO. Because they equal the same thing, those must be equal to each other. PSK equals 90, that is the transitive property. It's going to be used a lot in our proofs throughout geometry. And then from there, we have Kn being perpendicular to Qt. Let's see why this is true. PSK, again, in our figure, is that bottom green dot there. Let me zoom in a little bit for you. PSK is where that bottom green dot is. We've now proven that that is a right angle. It's 90 degrees because of our transitive property. And that is the proof we need for perpendicular lines. Perpendicular lines have to intersect and form a right angle, and we just proved there's a right angle at that intersection. Right, so the reason that we can say now that our lines are perpendicular is because perpendicular lines intersect at right angles. It's possible that we have proofs involving perpendicular lines only with no parallel lines involved at all. And that's what's happening here. We're told angle 1 is congruent to angle 2. And we have to prove with that information that line G here is perpendicular to line H. That should say perpendicular there, not parallel. Need that symbol instead. That was my mistake. Sorry about that. Like always, our proof starts with given information, right? We are told angle 1 is congruent to angle 2. That's the first thing given in our proof. This is true because it was given to us. Now, we know congruent means equal in measure, so if I know these angles are congruent, I can also say they're equal to each other. Technically, there should be m's there to say the measure of angle 1 equals the measure of angle 2. That's true because we know the definition of congruent angles. Next, we're told angle 1 plus angle 2 equals 180 degrees. Well, this is an angle pair that we learned back in Unit 1 that we need to know. Unfortunately, students forget the name of this often. 1 and 2 here are side by side on a straight line. This is a linear pair. Linear pairs are supplementary to each other. So we can say 1 plus 2 equals 180 because we know linear pairs are supplementary to each other. Linear pairs are, I'm going to abbreviate, supplementary to each other. Okay. Next, it says angle 1 plus angle 1 equals 180 degrees. Notice, very similar to that equation, just instead of an angle 2, there's another angle 1. Well, I've done just some substitution. I know the measure of angle 1 equals the measure of angle 2. So I've just substituted this angle 2 for another angle 1. That's the substitution property. So remember, that's going to be used whenever you say two things are equal and you swap them for each other in an equation. That's going to be the substitution property. Substitution property. All right, next, we have a funky looking statement here. We're not used to seeing that in proofs, right? But this really isn't any different than algebra and combining like terms. Instead of angle 1 plus angle 1 equals 180, if it was like x plus x equals 180, we would just combine those x's and I'd have two x's. And that's exactly what's happened here. There are two angle 1s. So this is combining like terms that we've just done. You may often see this written as simplify as well as the reason here. I like writing combine like terms. This is true because we combined like terms. All right, our next statement says angle 1 equals 90 degrees. If I keep going with this algebra I'm showing you here in red, to get x by itself, I would divide both sides by 2, and I would get 90 degrees. The same thing would happen here. If I divide both sides of the equal sign by 2, I'm going to get 1 equals 90. So that is the division property of equality being used there. Division property of equality, right? Then it says angle 1 is a right angle. Well, we should know that. Right angles are 90 degrees, right? So we can literally just write that. Right angles are 90 degrees. So if I say an angle is 90 degrees, I can say it's a right angle because I know right angles are 90 degrees. And again, that's the way that we prove lines are perpendicular to each other. Again, that should be a perpendicular sign, not a parallel sign. That's my bad. Because they intersect at a right angle, I know that they are perpendicular to each other. All right, so just like our last proof, because I proved angle 1 was a right angle, I can say the lines are perpendicular because perpendicular lines intersect at right angles. We're going to wrap up today's lesson with this last little example here. This is kind of a just-in-case thing here. We have a very strangely worded question. It says determine the values of x and y that make these segments perpendicular to each other. So like right now, there's no proof in the figure that these are perpendicular because there's no right angles anywhere. Perpendicular lines intersect at right angles. But it tells us to solve for x and y in a way that makes them perpendicular. And that's really just a fancy way of saying, hey, assume these lines are perpendicular and solve for x and y, right? So we're treating it like these are right angles. So that means we can have two separate equations here to solve for x and y. Because yes, I know linear pairs have to add up to 180, but I can't have the y and the x, two different unknowns, in that same equation. But I do know that because we're treating these lines as perpendicular, each of these angles has to equal 90. So I can use the equation 11y plus 2 equals 90 to solve for y. To get 11y by itself, I would subtract both sides by 2 to get 11y equals 88. Then I would divide both sides by 11 to get y equals 8. And I can do the same exact thing over here for the x, because those are at a right angle if these lines are perpendicular to each other. So we have x squared plus 9 equals 90. I'll get x squared alone by subtracting both sides by 9, so I get x squared equals 81. We haven't seen this algebra yet in geometry, but to get from x squared to just x, like we would anywhere else in algebra, we need to do the opposite of what's happening to our variable to isolate it. So the opposite of squaring it would be square rooting it. So if x squared equals 81, then x would equal the square root of 81, which is 9. Guys, that wraps up our lesson today on proofs. Remember, proofs is that it's a difficult thing to grasp, and we're going to be working on it all year long. So you shouldn't expect mastery right now with proofs. You probably still are struggling with things like the transitive property and coming up with reasons for true statements. But we're going to keep revisiting it and revisiting it in every unit. We're going to keep getting practice. Eventually, you're going to get really comfortable with it. But again, that wraps up our lesson for today. I'll see you in the next one, guys. Bye.